Today, Physical Science 102, we're going to look at chapter 14 in our textbook on the topic of organic chemistry. This is a pretty tall order because organic chemistry is an extremely large field of subdivision of chemistry. But we'll do our best to get the fundamentals in. So we're going to work from PowerPoints as usual. And so I'll share the PowerPoints right here. There you go. Make a slideshow out of it. There we go. Now let's see. I want to make. There we go. I'm going to make my image a little bit bigger so I can see what I'm doing. Okay. There are only 5 sections in this chapter, but it covers a lot of ground. So let's get to it. Organic chemistry. Organic chemistry, by definition, is the study of the chemistry of carbon compounds. But it's more specific than that. In fact, an organic compound must have at least these 2 elements. Carbon and hydrogen. Just because it has carbon doesn't make it organic. It has to have hydrogen bound to the carbon also. So the reason I say that is because this compound, carbon dioxide, has carbon in it, sure, but it's not organic. Not by our definition. So it would need to have hydrogen in there somewhere. Say the simplest organic compound is methane. That's organic. Okay, we'll get to more of that in a few minutes. So where do we find organic compounds? Organic compounds are in living systems. That could be animals, it could be plants, it could be microorganisms. Originally, organic compounds were only in living systems. But in the modern age, organic compounds now are regularly synthesized without any living systems being involved. Some of those might be nucleic acids, right? The foundation compounds for DNA and RNA. Proteins, what you'll find in muscle is protein. Those are organic compounds. Fats are organic. Carbohydrates, and we'll have to define what these are at some point in the lecture. Then we can identify various enzymes that are organic. Certain vitamins are organic. Hormones, these are all organic compounds. Now, more a narrowed study of organic compounds is biochemistry. And the study of biochemistry is actually a study of organic compounds and their behavior in living systems. We want to understand how the chemistry works inside biological systems. But we need the basics of organic chemistry before we can even move into biochemistry. Originally, historically speaking, scientists thought that organic compounds were some special kind of substance that had within it what they called a vital force that caused them to be different than any other compounds. that may be investigated. But that was disproved in the middle of the beginning of the 19th century by Friedrich Wöhler. And the story is a little bit too involved to go into right now, but suffice it to say, the vital force theory was debunked and is no longer active. Organic compounds are just like any other chemical compound. They're built the same way. We just specify which elements are allowed. Well, we are going to have a little bit of detail from Wöhler. He successfully synthesized the compound urea, which originally had been isolated from living systems. It's commonly found in urine, but he synthesized it from inorganic compounds. Urea looks like this. Okay, it's a nitrogen-based compound with carbon. So we have hydrogen, carbon, and then other elements. So this is an organic compound. This is the waste product for many animals when we ingest nitrogen-based compounds like the nucleic acids and proteins in particular. When we ingest those, we use those to build our systems and to make things that are essential for cellular activity. But there are always waste products. We have extra nitrogen in our system. We've got to get rid of it because it can become toxic. So our bodies form, all mammals do, and some cold-blooded animals also make urea. But this way we can get rid of 2 molecules or 2 atoms of nitrogen per molecule of urea and get rid of that nitrogen waste product. Okay, so this vital force theory is no more. Organic chemistry, like I said before, is a huge field of study. And hopefully it will become obvious why that is as we proceed. Because so many compounds with specific, engineered, in fact, characteristics are possible simply by the way we combine carbon and other elements that go with it. Okay, so let's start with the basics. How do carbon compounds bond with other elements? We look at how carbon can bond with other carbons, how carbon can bond with hydrogen and oxygen, nitrogen and sulfur, and some halogens. Remember, the halogens are like fluorine, chlorine, bromine, and iodine. They're very important in synthetic organic chemistry. It's important to recognize that carbon is a nonmetal, and all of these other elements that I've mentioned at the beginning of this slide are also nonmetals. Remember, when you get nonmetals and nonmetals bound together, they have to bond covalently. That is, they share electrons when they bond. So that's just the way it is with non-metal bonding. But that's an advantage because non-metal bonding usually produces very strong bonds, and the result is unique molecules that act independently, as opposed to ions that can interact with any other ion based upon their electrostatic charge. So we actually have molecular chemistry going on here because of the covalent bonding. So I'm going to show you a table in the next slide, and it references how these compounds can form. All right. When we consider bonding with carbon, for our purposes, carbon should have 4 bonds. Now, more advanced study of organic chemistry will allow you to reduce those number of bonds and for other purposes. But at this point, the most stable compounds always have 4 bonds to the carbon. So the carbon has 4 bonds. Nitrogen will have 3 bonds. So when you build an organic compound, all you have to do is be sure that carbon has 4 bonds of some kind. They could be 4 single bonds, they could be a double and 2 singles, or they could be a triple and a single. I don't know of any carbon compounds that have 4 bonds to the carbon. I mean, a quadruple bond, right? Triple's the maximum. Nitrogen can have 3 bonds. It can have 1 and a double bond, or it can have a triple bond, and that's it. Oxygen and sulfur also will only have 2 bonds, and they'll be satisfied. So it'll be 2 singles or 1 double. Hydrogen and the halogens all only single bonds. So if we remember these rules and follow them when we start to build compounds, then we are less likely to make mistakes. Now, why is that? I think we've already introduced the concept of the octet. So when you look at carbon and you say, how many valence electrons, how many outer shell electrons does it have, and how many does it need to complete its octet? So carbon has 4 valence electrons. That means it needs 1, 2, 3, 4 to complete the octet. That's why it has 4 bonds in any of these organic compounds. Whereas nitrogen has, it already has 5 valence electrons, so it only needs 3. That's why 3 bonds are characteristic of nitrogen in any of these organic compounds. And you can make the same argument for oxygen, which only needs 2 electrons to complete its octet. And hydrogen, of course, hydrogen only has 1 to begin with. So it's not an octet rule, it's a duet rule. So hydrogen only needs 1 electron to complete its outermost shell. But all the halogens only need 1 electron each. That's why they only have 1 bond for each one. 2 electrons per bond. One comes from for instance, carbon. And then you could have, even if you have another carbon, then you could form a single bond between 2 carbons, but then 3 valence electrons on 1 carbon, 3 on the other, require 3 more bonds. Now they can make the bonds again between the 2 carbons and then make another one. So you can have 3 bonds between those 2 carbons, but you still have 1 valence electron on either carbon that needs to be satisfied to make the octet. Okay. So with those rules in mind, here are some examples of organic compounds. So which one represents a real compound? And that's based upon these rules. Carbon has 4 bonds, nitrogen 3, oxygen 2, and hydrogen only 1. and halogen's only one. So we look to see. Okay, let's see about this. In structure A, each hydrogen and halogen has one bond. That's good. Carbons, how about the carbons? This carbon has 4 bonds. This one has 4 bonds. This one has 4 bonds. That one has 4 bonds. That's a valid compound. Okay. So what's wrong with the other one? Well, let's see. This hydrogen has 1. That's good. Oxygen's got 3. Can't do it. It won't work. So that nitrogen has 3. This carbon has 4. That carbon has 4. We're focused on the oxygen because it can only have 2 bonds. All right. So that's not a valid structure. How about this one? Let's see. Notice that instead of straight lines or just branches, we have actually a cyclical compounds. In other words, they form a daisy chain. This one has 6 members, and then 2 of these members are part of this one, which has 5 members. So we check the number of bonds. Well, let's see. Whenever you see carbon and hydrogen written together, like this, CH3, for instance, the hydrogens are always bound to the carbon. Right? So the authors have been careful to make this bond between the carbon and nitrogen, so we show that the hydrogens are out here bound to the carbon. These hydrogens are bound to the carbon. So let's see, we got 1, 2, 3, 4. That carbon's good. This nitrogen's good with 3. This carbon is not good. It only has 3. That oxygen's not good. It only has 1. This one's okay. That one's okay. This one's only got 3. This one's only got 2. This one's only got 3. So this is not a valid compound. It violates several of the rules, right? And this slide just shows where those violations occur. That's not a valid structure. It's supposed to be about a structure of caffeine, right? But as written, that structure is not correct. Okay, so now that we know how many bonds each of the elements can have and should have in an organic compound, we'll look at the various classifications of organic compounds. And the first one is actually the simplest type, hydrocarbons. Hydrocarbons are just what it says, carbon and hydrogen. That's all there is in the compound, just those 2 elements. Now, these compounds can also be divided into, they can be aromatic compounds, which is a special kind of cyclical compound where they have the daisy chain. They have a special character. Now, in this text, in our discussion, we're going to limit aromatic compounds to the benzene ring. And I'll show that to you in just a second. But just be aware that aromatic compounds can be what we call heterocyclic. That is, they don't have to have just carbon. They could have carbon with maybe a nitrogen in there and maybe a sulfur in there. So there are other characteristics that define aromatic compounds. But in this course, we don't have time or the need to go into those definitions. So we'll just limit our discussion of aromatic compounds to the benzene type. And I'll show you what that is in a second. Aliphatic hydrocarbons. Those are chained carbons. In other words, start at one end, go to the other, and you're done. You don't start at one end and go in a circle, in a chain. So that's the basic difference between those 2. Okay. The aromatics in this group, the aliphatics in this group can also be subdivided into other groups. The aliphatic carbons, hydrocarbons, can be alkanes, alkenes, alkynes, and cycloalkanes. So we can have cyclical aliphatics. They're just not aromatic. Okay, so this is not going to make a whole lot of sense until we actually show you some, define what they actually mean. But that's a classification tree. Okay, we're going to go to the aromatics first and talk about benzene. Benzene is a ring compound, and it's composed of 6 carbons in a ring. So we could say, put 6 carbons here and bond them together. Right? Now, as written like that, that's not good enough because there are only 2 bonds each, right? Okay. So what if we put hydrogens on each one of them? Right? We could do that. Okay. Now they have 3 bonds each, and the hydrogens only have 1, which is fine. How are we going to get 4 bonds for each carbon? One way to do it is to make a double bond. Right? If we put a double bond here, that gives 1, 2, 3, 4. That carbon's good. But if we put a double bond here, that makes 5 bonds for that carbon. We can't do that. So we alternate. We skip this one and go to that one. Now this carbon has 4, that carbon has 4, this carbon has 4. All we need is another double there. Now this one has 4 and that one has 4. So that's one way to represent benzene. And in many respects, benzene is the most important aromatic hydrocarbon. But it's dangerous. It's a cancer-causing agent. So its use is restricted. It's in pure form, benzene is a liquid, and it has a distinct odor. It has a kind of a sweet smell, and that's just the way that benzene reacts with your olfactory senses. Many organic compounds that are either liquid or gas affect your olfactories in different ways, and they're characteristic ways. I think we've discussed Lewis structures. In fact, I'm going to look and see if we have, because if I say any more about Lewis structures, I want to be sure that the topic has been introduced somewhere else. Let's see. 41. Yes. We have introduced Lewis structures. Actually, it was in chapter 12. But did we define how to draw a Lewis structure? That's the key. Or are we just going to have to memorize them? I don't see any rules here for Lewis structure. So it's not like you can just take any compound and draw the Lewis structure. These structures are named, this method of drawing structures, organic, inorganic, it doesn't matter, are named after G.N. Lewis. He was an American chemist, and he was looking for a way to simplify the representation of compounds and how they interact with them, how they bond. So he based his structures on the octet. And we've talked about the octet already. But since we haven't introduced the Lewis structures in terms of the rules involved in drawing them, we just have to introduce them and say, this is a Lewis structure, take it at face value. There are a number of different ways to write benzene. This is the complete structure where you have all of the atoms identified, all of the bonds identified. But it can get kind of unwieldy when you start drawing larger structures using this as a subunit. So one way to simplify it is this Kekulé symbol. Kekulé was another chemist who actually proposed the correct structure for benzene. For the longest time, chemists couldn't figure out, they knew how many carbons were there, but they didn't know how they were arranged. So lots of different structures were proposed. And it wasn't until Kekulé proposed this ring structure that the mystery was solved. Now, he claims that he had a dream of a snake in his dream, and the snake grabbed onto its tail and made a ring. I don't know if that's true. That's just the story. But be that as it may, this structure was valid and solved many problems with using these organic compounds. Now we know that these aromatic compounds have a way of sharing electrons. They sort of smear the electrons out over the entire structure. And we represent that, rather than these individual double bonds, we represent that with a circle. The reason for that is, if this were true, right, single, double, single, double, single, double, then this would be a different bond than that one would be. In fact, double bonds are stronger and shorter. So if this were true, that would be kind of a lopsided molecule. You would have a long distance here and a short here. But in fact, laboratory experiments have proven that all of these bonds are the same length and the same strength. They're exactly alike. So each one has some double bond character. So that's why we represent it with this ring, to show that all the bonds are equal. But that gives the benzene ring structure stability. It is very difficult to break into that ring. Okay. Notice one other thing about these simplified structures. There are no carbons written. There are no hydrogens written. Whenever two lines in an organic compound come together and meet, like this one right here, that is a carbon. The only time it's not a carbon is when we actually put a different atom there, different element. We might put a nitrogen there. We might put a sulfur there. But if there's no explicit symbol, it's always a carbon. And then wherever there are carbons, you need 4 bonds. So if there's nothing given that's bonded to make that 4th bond, we always assume it's a hydrogen, right? So this carbon right here will have 2 carbons bonded to it and a hydrogen right there. That's just the shorthand. You can imagine if we start to build large molecules out of these subunits, that having all these C's and H's in there would just make a mess. It's easier to see what's happening in the molecule if we use the abbreviated version. Okay, other types of aromatic compounds. In this one, toluene, we have substituted a carbon and 3 hydrogens for that 1 hydrogen. right? So this carbon, and when we do that, sometimes we explicitly write the carbon in. In this case, we did. Sometimes we don't. Sometimes we just say this. And if we do that, we know that out here is a carbon and 3 hydrogens. Or if we do that, we know now that's a carbon and that's a carbon. This one now only has 2 hydrogens because it's got a bond here and a bond here. It only needs 2 more. And this one only has 1 bond to the carbon, so the others are taken up by 3 hydrogens. Okay. That's the shorthand notation. Sometimes we can get these benzene rings to fuse together, right? So naphthalene is a fused double benzene ring. So it shares this carbon here and this carbon here with the 2 rings. So we got a benzene ring here and we got a benzene ring here. Phenanthrene is another example where you have 3 fused rings like that. These are just examples. Oh, and if you're looking for naphthalene in on the grocer shelf, look for mothballs. In fact, there are 2 types of mothballs. Naphthalene is one of them. There's another one. Let's see. The other compound escapes me for the moment. Phenanthrene is used commonly in various types of dyes, drugs even. It's precursor for drugs, and you can form explosives from it also. Here's what I was talking about, the benzene ring, where electrons are delocalized in sort of a cloud above and below the ring. And by sharing all these electrons around that ring and making every bond exactly the same length and strength, we stabilize the molecule and make it very resistant to attack. Okay, here's another substituted ring. Right? There's your benzene ring. Now, instead of a hydrogen here, we have an NO2, a nitrate group. One here, one here, one here. And then we have this, remember toluene had this one here. Well, this is a useful compound called trinitrotoluene, TNT. It's an explosive. So if you add a little energy to this molecule, it will spontaneously decompose and give up a huge amount of energy and form lots of gases, which creates that overpressure that all explosives need to do their job. Okay, so how do we build a molecule from the name? Right, these conventions are based upon rules that are set out by IUPAC, the same group that helped us name binary compounds in an earlier chapter. So they have rules for organic compounds too. In this case, the organic compound is 1,3 dibromobenzene. So if we write the name like this, okay, the way to deconstruct that and turn it into a structure is to start from the root. This is the base unit. So we would draw the benzene ring. And then we also know that on this ring are positioned 2 bromines, 2 BRs. And this tells us where those 2 BRs are supposed to go. Now, with this, the way the structure is written now, all of these carbons are equivalent. So you just have to pick a starting point. So if we say this is our starting point for 1, 2, 3, 4, 5, 6, then 1, 3 position, we'll have a bromine right there. Okay. Now the convention says that if you were to put these bromines here and then number the other direction, 1, 2, 3, 4, 5, 6, that would make this 1,5 dibromo. But the naming convention says you use the numbering system that gives you the smallest numbers. So 1, 3 is smaller than 1, 5. So we would number this way. Or if we did number this way, that bromine would have to go over here on the 3. Okay. So we drew the benzene ring. We know we've got a bromo there. That identifies position 1. Then the second one is we work our way around clockwise. Usually clockwise is preferred when you can. And we work our way around to the 3 position and put the other bromine. That's the correct structure for this name. Okay. So this is supposed to be an organic compound, right? Because it has carbon and hydrogen. Only in this case, well, and the carbon has to be bound to the hydrogen. So hydrogen cyanide, which one of these is best? We can look at it 2 different ways. One is, how about the number of bonds? All right. If we look at carbon in B only has 3 bonds, so we throw it out. Carbon in C has 2 bonds, and nitrogen only has 1. That's wrong. How about D? Carbon only has 3 bonds, and the nitrogen only has 2 bonds. That won't work. So A shows carbon with 4 bonds, nitrogen with 3 bonds, hydrogen with 1 bond. That's the correct one. HCN. That's our correct structure. Okay. So this one, excuse me, is already written for us. So if you have, this one had 2 bromos, so we just said dibromo, means 2 bromos. But if we have a different attached atoms, then we would identify each one with its position. So in this case, the description is, let's see, let's go down to here. This one is 1 chloro, 2 fluoro. 1 chloro, 2 fluoro. Benzene. Oh, not that one. Okay, how do we know which one to put first? We go alphabetically. So the chlorine is number 1 and the fluorine is number 2. And we would say this position is number 1, so that's where our chlorine goes. And this position is number 2, that's where our fluorine goes. Okay. Okay, so let's move away from the aromatics for a moment and talk a little bit about the aliphatic compounds. Oops, scoot that back a little bit. There we go. No benzene rings. We can have cyclical structures, but they're not aromatic. So we always start with the alkanes. They're the very simplest. Then we can take the alkane, which is a straight structure or a branched perhaps, and then turn it into a ring structure for cycloalkanes. Then we can take the alkanes and put a double bond in there and make an alkene, or we can put a triple bond in there somewhere and make an alkyne. So that's the progression. That's why we start with alkanes, because the rest of them are built upon the alkane structure. All right. So alkane hydrocarbons only have single bonds, right? And they're what we call saturated. That just means that they're all single bonds. That's another word for single bonds is saturated. It actually has something to do with the number of electrons that are incorporated into those bonds. But let's leave it at that. And consequently, the number of hydrogens are at a maximum. Can't have any more hydrogens. So when we write the formula for an alkane, we have the number of carbons, and then we can calculate the number of hydrogens based upon this formula, right? We can take the number of carbons, multiply it by 2, and add 2, and that's the number of hydrogens. Or notice, mathematically speaking, you can factor out that 2. You can say n plus 1 times 2. So for instance, if we had 3 carbons, how many hydrogens will we have? 3 plus 1 is 4 times 2 is 8. Right? And we can prove it to ourselves. This alkane would have carbon, 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 and then hydrogen, hydrogen, hydrogen in each one of those positions. 1, 2, 3, 4, 5, 6, 7, 8. Okay. And that formula works for any alkane. And all we need to name an alkane is to know how many carbons. And we use the Greek prefixes, right? Except for methane. Methane is a special name to itself. Actually, the first 4 alkanes have special names. And then after that, we start using the Greek prefixes and add A-N-E on the end. Well, they all end in A-N-E, but only from pentane, 5 carbons, do we start putting prefixes for the number of carbons. Up to that point, and I think this is grandfathered in from pre-modern times. 1 carbon is methane. 2 carbons is ethane. Okay. 3 carbons is propane. That's the same stuff you barbecue with, propane gas. This is butane. Right? Cigarette lighters, butane lighters, same stuff. And then we go beyond that. We start with pentane, hexane, heptane for 7, octane for 8, nonane for 9, decane for 10, and goes on and on. Notice that up to butane, all of the alkanes are gases. So these are all gases. Then when you get to pentane, you start creating liquids. So from pentane up to decaheptane, those are liquids. And beyond that, the decaoctanes are solids. Okay, so here's a list of some of them. Let's see, 4, 5, 6, 7, 8, up through octane, this list. And it shows this is a condensed structural formula. So what do we mean by that? Well, that just means that we're showing some of the structure, the characteristics of the alkane. So let's take butane. This is the molecular formula for butane, but it doesn't tell us much about the structure. If you don't know that that's butane, it could be other possibilities. So this would be, you always have a CH3 on each end, right? That's called a methyl group, named after this one. And then here, if we draw that, remember that those hydrogens are not bound to the next atom. They're bound to this carbon only. So that carbon is bound to the next carbon. And then you can write it like this, right? 4 carbons, right? 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. 4 bonds each. Or you can do like they did and take this one and say you need 2 of them. And they're in a line. Okay. This is what ethane would look like. Notice that when you actually look at the 3-dimensional structure, rather than this flat plane, what you find is that these bonds around carbon are pointing off in 4 equal directions, actually to the points of a tetrahedron. Right? So if you put the carbon in the center, then it would form a bond with this one, that one, and the one behind it, whatever they might be, in this case, hydrogens. Right? That's the tetrahedral structure, and it's characteristic of all alkanes. All the carbons have a tetrahedral symmetry. All of these, tetrahedral symmetry. Sometimes we call it the ball and stick. It's a 3-dimensional model. If you have a model, right, organic model at home, you can play around with these and see what they look like. In organic chemistry, the behavior of one organic molecule with some others or other organics depend in large part due to this 3-dimensional structure. That's how they behave. And notice that when you have a single bond, right, you can take this group right over here and rotate it, right? It can spin around that single bond. Later, when we get double bonds in here, the double bonds lock those things in place. They cannot spin now. But as long as they're single bonds, they can spin. Okay, there's the tetrahedral structure, right? We've drawn the tetrahedron in dotted lines. Those dotted lines don't represent bonds. They represent the outer limits of the tetrahedron. The bonds are actually internal here. And the angle on those bonds is 109.5 degrees for the perfect tetrahedron. This is a ball and stick model. Here's the space filling model. Okay, where do we find these things? Well, natural gas is methane, right? If you heat your home with gas, or if you cook with gas in your stove, or your water heater is gas, natural gas is predominantly methane. Propane and butane both come bottled. Propane, most people have the 20-pound tanks when they're barbecues. Some homes are heated with propane, and they'll have bigger tanks outside that are periodically filled by the vendor. Butane is less common for heating homes. You'll find it in cigarette lighters. Some forklifts and cargo handling equipment will have engines that run on butane. Gasoline. Gasoline is a mixture of different alkanes. In fact, it's more than just alkanes. But the primary alkane in gasoline is octane. But you can have a mixture of pentane, some hexanes, heptanes, octanes, nonanes, decanes. And those blends of these compounds are specific for regions of the country and for times of the year. In the hotter seasons, you'll have more of the heavier components. And in the colder months, they'll blend gasoline with more of the smaller compounds, pentanes, hexanes. That's so that the gasoline, when it goes into your engine, will vaporize correctly. Kerosene, right? It's an alkane that has carbon numbers from 10 to 16. So it's a mixture also. Anything greater than 16 fills in these other possibilities. Remember the alkanes that are greater than 16. Let's see. Let me back up a little bit. Where is it? Here we go. Up to 17 are liquids. Anything greater than 17 is solids. Okay. Oops. Okay. So where we have up to 16, we've got liquids. And then the greater than that should be solids. But I see some solids in here. Diesel oil, diesel fuel, fuel oil. Some houses, particularly in the northern states, heat their homes with fuel oil. Petroleum jelly, paraffin wax, lubricating oil, even asphalt is formed from alkanes. That's why when asphalt is being laid on a road, it comes out hot. In other words, they heat it up so that it'll flow. And then as it sits and cools, it solidifies. And it's not just pure asphalt on the road. It's a mixture of asphalt and what they call aggregate. It's a mixture of different sizes of rocks and sand. And the asphalt is there just to hold all that stuff together. Okay. We can find alkanes all over the place. Paints, plastics, drugs, detergents, insecticides, even cosmetics. You put alkanes on your face. But actually, a small amount of the production of these petroleum products are for these products. Most of the alkane production goes to energy. They're burned in some form or another. Now, alkanes are generally not very reactive, except in the proper atmosphere and with the proper activation energy. If we kick them with, say, a spark of some kind, and there's oxygen in the atmosphere, then they will burn. And it takes a good amount of activation energy to get them started, because these carbon-hydrogen and carbon-carbon bonds are very strong. Okay, so before we leave the alkanes, sometimes the alkane and other molecules, actually, organic molecules, are built with branched groups. And when that happens, we change the name of that group from ANE to YL, alkyl group. So from methane, we get methyl. From ethane, we get ethyl. Remember when I drew that structure? Or actually, the book showed you this one. Right? Toluene. This is 1-methyl benzene. We say methyl rather than methane. 1-methane benzene. No, it's 1-methyl. Or actually, we just say methyl benzene. Because if there's only one of them, then any place you put it is the one position. So this would be, it's given a special name, but it's also methyl benzene. Okay. And if we put a CH2, CH3 out here, it would be ethyl benzene. Okay, so if you want to form a YL group, an alkyl group, all you have to do is drop one of the hydrogens and leave an empty bond there. That's where you bond to some other molecule. So this is the methyl group. This is the ethyl group. You can have a propyl group. You can have a butyl group with 4 carbons. You can have a pentyl group with 5 carbons. Okay, so why are we telling you this? Because the alkanes are not all straight chains. We showed you a homologous series of straight chain alkanes, right? From methane, ethane, propane, butane on up. But like I mentioned earlier, you can arrange these carbons in a number of different ways. In other words, you can have 4 carbons in the molecule, in the alkane, but they don't always have to go in a straight line. We could have 3 carbons in a straight line, and then we could have another carbon off branching, right? And if we put the hydrogens in here, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. C4H10. We still have that same formula. N plus 1 times 2 number of hydrogens. But in this case, the carbon branches here rather than being on the end. That's called an isomer. Now, isomers in organic chemistry are different than isomers in physics, right? We talked about atomic isomers, where you have a different number of neutrons. One atom has so many neutrons, another atom has a different number, but it's got the same number of protons, then it's an isomer of that element. But in organic chemistry, isomers take on a different meaning. And what we're calling constitutional isomers are often called structural isomers. In other words, they have the exact same molecular formula, in this case C4H10, but they have a different structural formula. Some of them only have one possibility. Like methane, it's only got 1 carbon, so that's it. Ethane has 2 carbons. There's no way to branch that one. Propane has 3 carbons. You can't branch that one because if you move one of the carbons over to another carbon, you still got a straight chain. Butane is the first alkane where you can start to get isomers. Now, this one is called isobutane. That's an archaic form of naming, but it's still used. So that's why I introduce it here. Straight chain butane is often called N-butane. So if we have that one, N-butane. The N stands for normal. Normal butane versus isobutane. Now, there's no ambiguity here because normal means this, iso means that, that's it. You can't have any other possibilities. So we don't really get into trouble when we say normal versus iso for butane because there are only 2 possibilities. Is when you start getting more carbons in the molecular structure that this naming convention breaks down and we need a different convention. Okay, so here's the ball and stick for normal butane or just butane. This is our isobutane, right? Like I drew it here, right? So this methyl group is attached to that carbon. And now, instead of calling it isobutane, the naming convention actually says you find the longest straight chain in the molecule, and that's your base for the structure. So this starts with 1, 2, 3 carbons, which is propane. So this would actually be starting with propane, and then where is the branch or a methyl group? Oops. Methylpropane would be proper. We could say 2-methylpropane, right? This would be 1, that would be 2. Or this would be 1 and that would be 2. Doesn't make any difference. Same thing. But the reason I can say methylpropane and leave it at that is because the only way you can make methylpropane is to put it in that position. It can't go anywhere else. If you put it out here, now you've got butane. So to avoid being redundant, we don't say 1-methylpropane, we say methylpropane. And in this case, that answers the question. Okay. So as long as you don't violate the octet rule, in other words, you give carbon its 4 bonds, give everybody else their number of bonds, then you can draw any structure you want. And any structure is possible. Now, of course, when you have a name, there's only one structure that can come from that name. So here's a list of the alkanes and the possible number of isomers that can be derived from this molecular formula. And notice here, butane is the first one where you can get more than 1. Now, butane has 2, pentane has 3 possible ones. Hexane has 5 possible. Heptane has 9, octane has 18. It starts to balloon the number of possible isomers you can get. And when you get up to 30 carbons, you could have 10 to the 9th, right? What is that? 10 to the 9th is a billion. You'd have over a billion possible isomers for that compound. Okay, so I've given you a taste of the nomenclature for organic compounds. Now we're going to get into it it's going to be in black and white now. Okay, so how do we name compounds? Like I said, you look for the longest straight chain of carbons. That's your base, the root for the name. And then you add the substituents, however many you have. And if they're all the same, you say how many of them you have. You have 2, you have di. 3 is tri. 4 is tetra, on up. Tetra, penta, hexa, hepta, octa, however many. But they have to be the same. Okay? And then you say, where are they on that chain? Where are they positioned? And it's a similar convention as the one I showed you for the benzene ring. You use the numbering system that gives you the smallest numbers possible. Okay, so we need some examples. How about this one? The compound name is 2-methylpentane. So what's the root structure is pentane, 5 carbons. So here we go, 1, 2, 3, 4, 5. And methyl is on the second carbon. So we put the methyl group on the second carbon right here. Now, what's to say we couldn't put it on this carbon? Well, we could, but in that case, you'd start numbering from the other end. Then it'd be 1, 2, 3, 4, 5 from that end. So putting it here or putting it there is the same molecule. There's no difference. It's in the number 2 position. Now, suppose we use a different substituent, like a halogen, right? For the halogen, we got the substituents named for the alkanes: methyl, ethyl, propyl, butyl, pentyl, hexyl, more and more carbons. For the halogens, Br, instead of bromine, we say bromo. Chloro for chlorine, fluoro for fluorine, iodo for iodine. So what if we wanted to draw this structure? 2,3-dimethylhexane. Hexane is the root. So we need 1, 2, 3, 4, 5, 6 carbons for the root. And we're going to put in 2 dimethyl, 2 methyl groups. One of them goes on the second carbon. The other one goes on the third carbon. Oops, there it is. So if we number from right to left, we say 1, 2. There's a methyl there. 3, there's a methyl there. Now, why did we put them on opposite sides? Well, that's sort of an implied arrangement, because these methyl groups are a lot bigger than hydrogens. So they're going to need more room. So we put them away from each other so they have more room. It's a concept called steric hindrance. In other words, in the 3-dimensional world, these things are going to want to be far from each other so they have room to operate. How about 2,2,4-trimethylpentane? There's pentane, 1, 2, 3, 4, 5. Okay, we need 3 methyl groups. 2 of them go in the second position and 1 of them goes in the 4th position. Okay, so 1, 2, 2 methyls here, and then in the 4th position, put this one. Now, why didn't we say start numbering from the other end? Say 1, 2. So that would be 2 methyl, 4, 4, 2, 4, 4 trimethyl. The reason is 2, 2, 4 is a smaller group. Instead of 2, 4, 4, we say 2, 2, 4. That's how we make this tiebreaker. right? If we number from the right, that gives us a smaller number set for more of the substituent groups. Okay, and then you add the hydrogens to fill in. And this is what that molecule would actually look like if we could blow it up big enough to see it, right? Here's your 1, 2, 3, 4, 5, your root structure, pentane, the backbone we call it. The backbone is 5 carbons, and then here's 2 methyl groups, and here's the other methyl group on the 4 carbon. Okay, now we'll talk about cycloalkanes. In other words, you just take a chain and connect the end carbons together, make a ring. That's a cycloalkane. And again, there are only single bonds between the carbons, right? We haven't introduced any doubles, any triples, no triples, no doubles, just single bonds. The smallest possible ring structure is formed from propane, cyclopropane. And its general formula is N for the carbon and 2 times N for the hydrogens. So it's no longer 2N plus 2. It's now just 2N. So let me show you why that works. So if we have a carbon, carbon, carbon like that, and we have a hydrogens here, 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 here. Okay, there you have C3H8. But if you're going to connect these 2 carbons together, you got to give up those 2 hydrogens. And now you're going to connect this carbon with that carbon and make a ring. Okay. And then this carbon needs 4, so we've got 2 hydrogens there, 2 hydrogens there, 2 hydrogens there. So the reason now it's 2N and not 2N plus 2 is because that plus 2 was lost at the end to complete the ring. Okay, here's cyclopropane in the condensed structural formula, right? I didn't have to draw those hydrogens in there because we know that each carbon has 4 bonds. So this one has 2 bonds, it needs 2 more, and those are filled by hydrogens. Butane, we can do the same thing, makes a square structure with the carbons. Cyclopentane, cyclohexane. Okay, just as a note, how stable are these molecules? Well, it turns out that cyclohexane is pretty stable. Cyclopentane is not too bad. Notice that when you form the ring, you're putting strain on that tetrahedral structure that we had as a linear. Now, the cyclohexane is perfectly tetrahedral, each of the carbons, no problem there. We have to bend it a little more to make the 5-membered ring, right? And then you really have to bend it a lot to get to the 4-membered ring, in which case we've gone to 109.5 down to 90 degrees. Okay, so that puts a lot of strain in the molecule, and it's even more strained for cyclopropane. Cyclobutane and cyclopropane are very unstable. In other words, they will decompose or react readily. Whereas cyclopentane and cyclohexane are not so much trouble. They're relatively stable. Okay, so here's this geometric structure for cyclopentane. And we can add substituents to it also. For instance, here we've got 1 chloro, 2 ethyl. Okay, alphabetical order. C comes before E. So 1-chloro, this becomes the 1 position. And then the 2 position is, if we go clockwise, is here. If we went counterclockwise, it'd be here. So are those different? No. All you have to do is take that molecule, flip it over, and you got the other direction. So they're the same. And 2-ethyl goes here. Okay. Now we can start adding double bonds. When you take an alkane and add a double bond to it, you get an alkene. And the general formula for alkenes with only 1 double bond present is the same formula as for cycloalkanes. Why? If you start with this, right, as our ethane, and you want to form a double bond, you've got to get rid of these 2. Right? So now you only have 4 hydrogens instead of 6. And you've got 4 bonds to the carbon, 4 bonds to the carbon, 1 each to the hydrogen. So we're not breaking any rules. It's just that now, to form that 1 double bond, you lose 2 hydrogens for the same reason you lost 2 hydrogens in the cycloalkane. This particular compound is called ethene or sometimes ethylene. So they're interchangeable. And all we have to do is change the ANE to ENE on the end of an alkane, and we get an alkene. If there's 1 double bond formed. Now, you can have more than 1 double bond in an alkene. I mean, it's not forbidden, but we need a naming convention that accounts for those other double bonds. We're going to stick to single double bonds right now, simply because there's not enough time to teach you everything there is to know about organic chemistry in just one lecture. So how do we say, where is that double bond located? If we prefix the root molecule, if we prefix it with a number, that shows where the double bond starts. So in this case, we've got butane to start with, and we put a double bond between 1 and 2. So we say 1-butene, right? We try to keep the numbers as small as possible. The second one is an example where we start the double bond at 2. So 2-butene is this one. So what if we moved a double bond over here and put a double bond on 3? Is that valid? Well, actually it's valid, but it's redundant, because look what happens. If we put a double bond on 3 and take that molecule and flip it over and lay it on top of 1-butene, you got the same molecule, right? So 3-butene is the same as 1-butene, and we don't say 3-butene because 1-butene is simpler, right? 1 is smaller than 3. So you actually have only 2 possible derivatives of butane with 1 single bond. Okay, now it's possible we could put another double bond over here at the 3, and then we'd have a double bond here and a double bond there, and that's perfectly valid. Then we would have to introduce a naming convention for that, and I'm not going to bother you with that, but I just want you to realize that we could do it. Okay, so if we have only 1 double bond, we're going to say ethene. It's only 1 possibility. That's 1 structural isomer for that one. I mean, yes, one structural isomer. Propene, same, only one. Butene can have two, one butene or two butene. And pentene, this is one pentene, but you could have two pentene and three pentene. If you went to four pentene, it'd be the same as two pentene, right? Just flip the molecule. So pentene can only have three isomers. This just makes the point. We don't say one propene, right? Because that's the only possibility. There's no other possibilities. And two things in naming compounds in chemistry is non-ambiguity. The name that's applied to a compound is for that compound and it's unique. No other possibilities. And we don't like redundancy either. Non-ambiguous and non-redundant. Okay, so what is it about alkenes? Well, you can make an alkene from an alkane, or you can go backwards. You can add those hydrogens back to this alkene. You can insert those hydrogens into this place and put one hydrogen on this carbon and one hydrogen on that carbon. And now you've got ethane again. We are resaturating the compound. This is known as an unsaturated hydrocarbon. When you have double bonds or triple bonds in the compound, it's known as unsaturated. Saturated compounds have all the hydrogens that they can hold, maximum number. This just shows that platinum is the catalyst for this reaction. And this reaction is used very often with certain types of fats and oils, naturally occurring fats and oils that are unsaturated. Industrially, companies will saturate those because when you do that, you change the melting point. You increase the melting point of an oil if you saturate it. And that's what business is like when they're frying food. They want an oil that will stand up to the heat. And if it's unsaturated, the smoke point is a lot lower. In other words, you can destroy, you can even catch fire, your oil, if you heat it up too high. But if you saturate it, you can go a lot higher temperature, which means you can cook foods faster. There are other problems with this that I won't go into right now, nutritional problems from saturated, artificially saturated hydrocarbons, oils, excuse me. Okay, alkynes. You just take the alkane and you put a triple bond someplace. And be sure that your carbon, wherever you put that triple bond, those carbons that are attached to it still have only 4 bonds. This is the simplest alkyne. Right? You can't form an alkyne with 1 carbon, right? That's impossible. But 2 carbons, yeah, you could. A triple bond with these 2. In this case, instead of N, for alkanes would be N, H2N plus 2. Alkenes and cycloalkanes are CN, H2N. That's it. We lost 2 hydrogens. In this one, we lose 2 more. Right? So if we say like this is our starting point with our hydrogens here. Then if we form an alkene out of this, ethene, but if we form an alkyne, we take those 2. Now we've got 4 and 4. This is also called acetylene. Welders use it. And I used to use it in my laboratory. One piece of equipment used acetylene to generate a flame. I won't go into the details, but it has multiple purposes, multiple uses. So if we got two carbons, so we say N is 2, so 2N is 4, right? Minus 2 is 2. So there we have CH2C, C2H2 is the simplest alkyne. If we used propane and put a triple bond in that one, that would be propyne. If we put a triple bond in butane, at the 1 position, it would be 1-butyne. In the 2 position, it would be 2-butyne. And this is an example of pentyne, 1-pentyne. Okay. Notice that if we say 5 here times 2 is 10, minus 2 is 8. Or if we said 5 minus 1 is 4 times 2 is 8. You can do it either way. Okay. And we can also resaturate alkynes, right? Ethine or acetylene can be resaturated with hydrogen using platinum as a catalyst. I'd be careful with this one. This is an extremely energetic reaction. Okay. So what are some other derivatives of hydrocarbons? You need what we call functional groups. Well, first you need define what a functional group is. It's any atom or any group of atoms that characterize that molecule. So a functional group could be some side branch, or it could be in the structure of the base structure. For instance, double bond or triple bond is a functional group, or attach an oxygen to it, to one of the carbons. That's a functional group. Let's see. Or these halogens are functional groups. OH would be a functional group. Methyl would be a functional group. A derivative of a hydrocarbon is one in which you have anything substituted in other than carbon and hydrogen. So if you substitute a halogen for a hydrogen, that's a derivative. Or if you substitute a nitrogen for a carbon in the structure, then that's a derivative. For instance, cyclohexane. Now this is not benzene. This is cyclohexane, right? So each one of these carbons would have 2 hydrogens. But if we substituted a nitrogen for that carbon, then that would be a derivative. And we would only need 1 hydrogen here. Okay, so that's a derivative, one type of derivative. If we take an alkane and derivatize it with halogens, we call that an alkyl halide. And it has this R is a place filler for some alkyl group, like methane or ethane or propane or whatever the case may be. And then X is a placeholder by convention. X is a placeholder for halogens. The reason we use those is because there are no elements in the periodic table with these symbols. So they're available. We can't confuse those with some other element. Perfect example of an alkyl halide is Freon, right? The chlorofluorocarbons. They have chlorine in them and they have fluorine in them and carbon, and whatever is left over is hydrogen. This particular example is dichloro-difluoromethane, and it's designated Freon 12, Freon 1,2. Now, the numbering system for these alkyl halides of this variety, these Freon type molecules, is kind of strange. I think I inserted a slide here with the rules, but it's not going to be something you're expected to remember. I mean, I don't even remember it, and I have to read the rules again whenever I want to decipher what Freon 12 means. But this is the molecule that's represented by dichloro-difluoromethane, or Freon 1,2, Freon 12. These are the rules, right? And they're a mess. I don't know who came up with these rules, but they're part of the system now. And they're not IUPAC. This is not an IUPAC system. Right? IUPAC uses the dichloro-difluoromethane. That's the IUPAC standard name for this compound. All right, so we'll skip over that. You don't need to learn it anyway. Just if you want to work with it, if you're thinking about becoming a refrigeration specialist, then you may want to learn that. Another example of an alkyl halide is chloroform, right? Everybody's heard of chloroform, right? It's an anesthetic. They used to put people to sleep for surgeries with chloroform. Had to be careful with it because you can reach a toxic level if you're not careful. But now it's known to be a carcinogen, and it has 3 chlorines and 1 hydrogen. So that's trichloromethane. Right? Carbon tetrachloride. We just put 4 chlorines around there. Carbon tetrachloride, or tetrachloromethane. And both of these have been found to be carcinogenic. Carbon tetrachloride used to be used as a dry cleaning agent. So you'd send your fine clothes off to be dry cleaned. That's what they would do. They would submerge them in their washing machines in carbon tetrachloride, and that would clean them without damaging the fibers. And then when you pull them out, you just, the carbon tetrachloride would evaporate. But the handlers of these compounds were coming down with some odd types of cancers and liver damage. So OSHA, Occupational Safety and Health Administration, and the EPA got together, and they decided that, nah, right, these are going to be strictly controlled. So you can only get these for laboratory experiments, or on an industrial scale, you have to have a bona fide need to use them in your manufacturing process before you can get them. Okay. So here's an example for drawing a structural isomer, constitutional isomer, for 2 alkyl halides with this molecular formula, C2H4Cl2. And notice when we write the formula, we write the carbon part of it first, and then we add the derivative elements afterwards, if they're not carbons. Okay, so where do we start? Well, the carbons are going to be bonded to each other. That's a given. And then they're going to be 4 positions around those carbons, right, for the bonds. So then we say, okay, where do the chlorines go? Well, they could go a number of places, right? We can't move the carbons around because there's only 2 of them. So we could put both chlorines on one carbon, or we could put a chlorine on either carbon. That's the only choice we have, because if we put 2 chlorines here, and then we say, oh, well, I want them to go over here, put them there, that's the same molecule. So they could either go here, like that, or they could go like that, right? And then you put the hydrogens in to fill in the spaces. So we have 1, 2, 3, 4, or 1, 2, 3, 4, right? Those are the 2 structural isomers with that molecular formula. Okay, so how do we name them? Well, we've got ethane as our backbone, and then we start numbering. Well, we want the smallest number possible. So this would be 1,1 dichloroethane. And this would be 1,2 dichloroethane. Okay. All right. Let's see. Oh, got another example. 2 constitutional isomers of C3H7F exist. Okay. I'll go for that. So let's spread these out a little bit. If there are only 2, then we got 1, 2, 3, 1, 2, 3. And we can have 4 bonds each. And this is what? C3H7F. Right? So we could put a fluorine on this end, or we could put one in the middle. We could put one out on this end too, but that would be the same as this one. Okay, that's why there are only 2 isomers of this formula, right? And then hydrogens fill in the rest. All right, there are your possibilities. One on the end, one in the middle. Okay. So this is just a reminder that these are still tetrahedral geometric structures. This would be 1 fluoropropane, and this would be 2 fluoropropane. Okay, more derivatives. Okay. This derivative we're talking about has hydroxyl as a functional group. So we take some hydrocarbon and we substitute OH for one of the hydrogens. And we name the compound based upon its alkane, and we change the ending to OL. So methane with an OH on it, this example, would be methanol or methyl alcohol. This, by the way, is the simplest alcohol of all the organic compounds, and it's also poisonous. Methyl alcohol is known as wood alcohol. That's a common name, and it's used in many products. Aftershave lotion. There's one particular one called Aqua Velva. It's kind of in a nice looking bottle. It's got a blue coloring to it that's added, and it was popular among winos. In fact, I used to live in Atlanta, Georgia, and went to their urban university, Georgia State University, which is right downtown. And they had green spaces scattered around, little pockets of grass and trees amongst all these big buildings. And a friend of mine and I, for one of our classes, went to one of these green spaces to do an ecology assessment. And while we were there, we were approached by, there's no other way to put it, an alcoholic. And he bummed a couple of bucks off of us, and then he went and joined up with some other of his friends, and we saw them. They were combining their resources, and they found they had enough money. They went over to the drugstore, and we could see as they came out of the drugstore, one of them had a bottle of Aqua Velva. So they would drink this stuff, and it would intoxicate you just like any kind of booze would, but it's poisonous. You really don't want to mess with it. Okay, this is the next alcohol up the chain, starting off with ethane. When we put an OH on the end of ethane, and it doesn't matter which side, right? There are no structural isomers here. This OH either goes on that one or that one, and it doesn't matter. It's the same molecule. This is ethanol. This is drinkable. It's used in, obviously, alcoholic beverages. It's used in some perfumes, some dyes. It's even used as a solvent for varnishes. And nowadays, we know that it's used in some of the hand sanitizers, usually about 60 or 70%. Now, the ones I don't like use the next alcohol up. Right, this is ethanol. The next one up is propanol. So it starts with propane, and then you can either add the OH on the end, like this, CH3, CH2O, oops, excuse me, CH2, CH2OH. So you can have carbon, carbon, carbon. You can put the OH out here. This would be normal propanol, or 1-propanol. This is the proper IUPAC name that says the OH is on the number 1 group. Or you can put the OH on the second carbon, and that would be 2-propanol. Those are the only two possibilities. Now, 2-propanol is, the other one was normal propanol. 2-propanol is often called isopropanol or isopropyl alcohol, and you'll find it in any bottle of rubbing alcohol. It has a very distinct odor, and it's distinguishable from ethanol. And it's unpleasant. So hand sanitizers with isopropyl alcohol in them are what I consider undesirable. But they're good disinfectants. They're sanitizing agents. Okay, so what if we take ethane and add 2 hydroxyl groups to it? In this case, we've got ethylene glycol. or 1,2-ethane diol. Right? So you put the di on the end for the functional group. So if you have 2 OHs, it's a diol. If you have 3 OHs, it's a triol. Okay. So in this case, we can only have 2 because it starts with ethane, only 2 carbons. You'll find this one in antifreeze. And it has a sweet flavor to it, they say. That's one of the reasons you want to keep it away from your dogs, because dogs have a sweet tooth. And if your dog drinks this stuff, it'll kill him. It causes their liver damage and the kidneys to shut down. Okay. So now we're going to move from aliphatic hydrocarbons to carbohydrates. Now we're working our way into biochemicals. Carbohydrates. Carbohydrates have carbon, hydrogen, and oxygen. And interestingly, the ratio of hydrogen to oxygen in carbohydrates is 2 to 1. Just like water, 2 hydrogens for every oxygen. So glucose is C6H12O6. 12 to 6 is 2 to 1. So that's why they're called carbo for the hydrogen and hydrate for the similarity to water. Now, this is not water inside the molecule, but the ratio is the same. So we call it hydrate for that reason. Here are 2 examples. Well, possibilities. All the sugars are carbohydrates, starches are carbohydrates, even cellulose that makes up trees are carbohydrates. Glucose is extremely important carbohydrate for our metabolism. Glucose is the currency in our bodies for transferring energy from digested food to all of our cells. That's glucose. So if you know anybody that's got diabetes, they monitor their glucose level in their blood plasma. If it gets too high, then you have consequences, serious consequences. Glucose is also the only molecule that nervous tissue will accept as an energy source, with one exception. They use ketone bodies for substitutes, but predominantly glucose for nervous tissue action. Whereas other tissues in the body, muscles, for instance, can use other compounds. Fructose, right? Notice fructose and glucose have the same molecular formula. They are isomers of one another. Fructose gets its name from fruit. It's commonly found in fruits. And if we take glucose and fructose and bond them together, you get table sugar, sucrose. You'll also notice if you read labels of the foods that you eat and the drinks, if they're sweetened drinks, very often they'll be sweetened with what's called high fructose corn syrup. So what happens is the companies that make it take cornstarch and break it down. Starch is a big molecule with lots of glucose units in it. And they'll take that and break it down and convert a lot of the glucose into fructose. The reason they do that is fructose is much, much sweeter than glucose to the taste. It's even sweeter than sucrose. It's sweeter than glucose, sweeter than sucrose, so they can use less of it and get the same sweetness out of their products. But it's not so good on your digestion. Oh, by the way, any of these carbohydrates, they end in OSE. So glucose, fructose, there are lots of other sugars. A common one is lactose, known as milk sugar. Let's see. Okay, so here we have glucose and fructose, and I said you could combine them and make sucrose, which is table sugar. What you have to do is form a bond between this carbon and that carbon by way of this oxygen bridge. So what happens is, in the process of forming this compound, the cell that does it removes one hydrogen from this side and an OH from that side and makes the bond link to that oxygen. Well, what do you have left over? You have two hydrogens and an oxygen, water. So for that reason, this reaction is called a condensation synthesis. Condensation from, you know what condensation is on the windshields of your car, right? If it's a cool night, you get condensation, you get dew condensing on your windshield. So that's where it comes from. This is a condensation synthesis. These structures are known as Haworth projections. And when you start getting into biochemistry and these larger molecules, it's difficult to make sense of their three-dimensional structure. So various methods of presenting them have been created so that you can see them sort of in quasi three-dimensional ways. So this dark line here is coming out toward you, and the other lines are going away from you. It's kind of like tilting it backwards a little bit to see the molecule. And notice that the ring structure here on these is, this one's 1, 2, 3, 4, 5 carbons and an oxygen. So this is what's called heterocyclic. In other words, they're not all carbons. We've substituted something in here, like that nitrogen before, heterocyclic. This one, however, has only 1, 2, 3, 4 carbons and an oxygen. So this is a hexose, and this is a pentose. Pentose meaning 5-membered ring, hexose meaning 6-membered ring. Okay, so here we're told again that fructose is the sweetest of all the sugars. It's found in fruits and found in honey. It's found in honey because when the honeybee collects nectar, which is predominantly sucrose, they carry it in their stomachs, and then they expel it into the hexagonal cell, and then they they spit in it. They inoculate it with an enzyme, which is called invertase. And it breaks that molecule apart and gives you glucose and fructose. And the reason they do that is that it's a preservative based on osmotic pressure. Did we study osmotic pressure? Let me see. I think we did. Well, I don't see it in the index, so maybe we didn't. But what it does is, by breaking the molecule apart, it increases the number of particles in solution and brings the osmotic pressure way up, so that bacteria and fungi cannot live in that environment. it will suck all the water out of them and they'll die. So it preserves. So that's why honey is the one food that is not, you don't have to preserve it. You don't have to seal it in a can. You don't have to add anything to it to preserve it. It's preserved as is. Okay, glucose, often called dextrose, is found in fruits, lots of different fruits, flowers, and in honey. And fructose is in honey also. Carbohydrates generally have to be broken down because the complex carbohydrates that we eat, like rice and pastas, have these complex starches. And the starches are long chains of these subunits hooked together. We call them polymers. So this long chain, this starch has 3,000 approximately units of glucose strung together. It's produced by plants. It's an energy storage medium. Seeds, tubers, which are underground stems, like Irish potatoes, and fruits store as starches. If you've ever grown corn, right? Field corn that you feed to cattle, when it's mature, all of the sugars that are in the seed are converted into starch. But if you like sweet corn is bred so that when you harvest the ears, each of the kernels still has lots of sugars in there, simple sugars, makes it sweet. And once you harvest it, they start to change. Once you pull that shuck, those sugar units, under the influence of enzymes in the cells, start to be converted into starch. So what you want to do is, when you harvest sweet corn in the field, you shuck it and throw it on ice, get it cold, stop that reaction. And then you can take it home and do what you want to with it. Otherwise, you're going to end up with corn that tastes more like starch than it does like sugar. Okay, cellulose is also a long chain polymer of carbohydrates, of glucose units. So starch and cellulose are both formed from glucose. Okay, so what's the difference? Well, one of the differences is the number of subunits. Right? How many units are there in that molecule? The other is, how are they bonded together? Right? When you get those, let's go back. Here we go. This is the number 1 carbon on that molecule. If you go around 1, 2, 3, 4, that's the number 4 carbon. If instead of fructose over here, you have another glucose on this side, then you can bond that carbon on the other one to this carbon on that one with this oxygen bridge. That's called a 1,4, a 1,4 linkage. Okay. For starch, the 1,4 linkage is twisted this way. The molecules are built like this, and then the other one is twisted back then. So they go like that, like that, like that, back like that, all down the chain. That's an alpha 1,4 bond. For cellulose, they're all the same. They just like that, and the bond is formed between them, and it gives them a different three-dimensional arrangement. That's a beta 1,4 bond. Okay, so what's so great about that? As it turns out, the alpha 1,4 bond, if you want to break those bonds and get the individual glucose molecules out of it, to use as energy source, then starch in our diet is okay. We can break those bonds. We have the systems inside that will break those bonds and give us access to those glucose molecules. That's why complex carbohydrates, starches, are massively intaken by marathoners and athletes because it's a concentrated energy source. If you eat cellulose, it goes in one end, comes out the other, just like it is. We often call that fiber. The reason it's not broken down is that beta-1,4 bond. The enzyme systems in our bodies cannot break that bond. It's just that simple. Now, if you want to break the bond, you need symbiotic microorganisms that have enzyme systems that will do that for you. And termites do have that. And some ants have that. Microorganisms living in their gut that produce the enzymes that will break those. So termites can eat wood, right? They eat right into your house, and they're doing that for energy. They break those beta-1,4 bonds with the help of their symbiotes, and they access the glucose in the cellulose molecules. Now, where do you find cellulose? In plant cell walls, right? That's the most common place. Cattle, ruminants that have the multi-chambered stomachs, they have symbiotic organisms in their rumen, and they can eat grasses and shrubs and whatever the case may be, and the microorganisms will help break down those cellulose molecules. They'll actually, they help break down the walls of the cell so they can get out the other stuff too. Right? But they can't do it on their own. They need the help of microorganisms to do that. Okay, other types of molecules, the amines. The amines are organic molecules that the derivative group is NH2. So we can say that if we have a methyl group and substitute an NH2 for one of the hydrogens, now we have methylamine. Okay, or if we substitute two methyl groups on that nitrogen, we have dimethylamine or 3-trimethylamine, right? So nitrogen always has these three groups bound to it, 3 bonds, right? In this case, we have 2 methyls. In this case, we have 3 methyls. So we haven't broken the rules. One characteristic of amines is they have very strong odors. It's easy to detect amines. We have the concentration of amine in the air can be very, very low, and we'll still detect it. 2 of the more noxious ones are formed by decaying flesh. Cadaverine is one. Putrescine is another. This is putrescine, which is a common name, a trivial name, we say. But if we give it the systematic name, it starts with butane here, 4 carbons, and then 2 amine groups. So 1,4-diamino butane is the proper name. Some amines are medicinal, right? Let's see, amphetamines are amines, and they cause the body to flood your blood with more glucose, and as the glucose level increases, you feel less fatigue, and you don't feel hunger. but there are some dangerous side effects, of course. Insomnia, weight loss, paranoia. And this is one type of amphetamine, benzedrine. And then, of course, there are illicit forms called methamphetamine is one of the most common. But I don't have that structure for you here yet. Okay, another derivative group, the carboxylic or carboxyl group, is actually an acid group. Right? And here's the group. It's based upon this carbon, right? This bond here goes to the root molecule. And then the carboxyl group itself has a double bonded oxygen, right? 2 bonds to the oxygen, 4 bonds to the carbon, 2 to this oxygen, and a hydrogen. So we have an oxygen, and a hydrogen. The reason it's acidic is this hydrogen is relatively easily removed in aqueous solution. So that makes it acidic. Okay, so the simplest carboxylic acid, actually, instead of another carbon out here, just has a hydrogen. Just stick a hydrogen on the end out there, and you get the simplest formic acid, or the systematic name would be methanoic acid. So carboxylic, when we make the carboxylic part of the molecule, it becomes the name and then oic acid. That's common. So this one is given formic acid name because formica is the Latin word for ant. And if you've ever encountered a fire ant, you'll know it. In fact, you never encounter one fire ant. There are always hundreds of them before you realize they're on you. And when they bite you, they inject formic acid, actually a cocktail of organic compounds, formic acid being a large portion of them, into that wound. And it burns. It's bad. You don't ever want to encounter fire ants. I spent 13 years in Baton Rouge and working, doing field research in Louisiana. And fire ants are very plentiful down there. They form these big mounds that are like 2-3 feet high. So those are the ones you can avoid easily. But the little mounds, you might, in tall grass, you might accidentally step on one. And if you step on a fire ant mound, they will come out of there. They're an army, right? Hundreds, thousands of them will come out. If you don't know that they're on you yet, they have a tendency for them to climb up your legs, inside your pants, and they won't bite you immediately. I think there's one of them, one of those fire ants has a bugle. And once they get enough of them on you, then he blows the bugle and they all bite at once. And then that's when you go running across the field, coming out of your pants. It only has to happen to you once, and then you're careful from then on. And I worked at the university there, LSU, and we would get graduate students coming through. And my boss, my major professor, would be their advisor, and I would be his helper. And we would caution these new students, especially those that are coming from northern states, said, watch out for these mounds, those fire ants, they're bad. And sure enough, every one of them, without exception, you'd see them run across the field coming out of their pants. Just one time. After that, they're careful. Okay, so that's formic acid. Acetic acid, we just substitute, instead of H, we substitute a methyl group. And that methyl group makes this ethanoic acid, or more commonly called acetic acid. And the reason it's called acetic acid is because this group here If it's lost its hydrogen, that's called the acetate ion. It's a polyatomic ion, the acetate ion. And then if you use the acid naming convention, then you add a hydrogen in aqueous solution, and that's when it becomes acetic acid. And if you have a 5% solution of acetic acid, you have vinegar. So everybody knows what vinegar tastes like. And obviously it's a weak acid, right? It has the sour taste, but it doesn't damage your taste buds, because even at 5% concentration, it does not dissociate lots of hydrogens into the solution. It's a weak acid. Then we have esters. So I look at esters. I look at esters like a derivative of a derivative, right? Carboxylic acid is a derivative, right? It has this functional group. So if we do this, and just say we have something out here, and then we have this carbon, that oxygen, okay? That's our carboxylic acid. If instead you have hydrogen here, you substitute another carbon functional group out there, then you have an ester, right? That's an ester. If you have a methyl group out here, that's a methyl ester. If you have an ethyl group, you have an ethyl ester, so forth and so on. Any of the alkyl groups will do. So these ester bonds, you can find them in nature, but you can also find them in the garment store or in the carpet store. Polyesters are based upon the ester linkage to form long chains. Naturally occurring esters. Contrasted to amines, right? The amines with the NH2s, they're very unpleasant odors. But esters have very, very pleasing odors. Many flowers and fruits produce esters. Very fragrant. And some of them have very nice tastes also. Okay, so here's an example of an ester. In this case, we have this group here with a carboxylic acid on it, right? You have a benzene, you have a hydroxyl, you have a carboxylic acid on it, and we form an ester with a methyl group. Okay, this is derived from oil of wintergreen. It's called methyl salicylate. So the methyl group is here, and the salicylate, or the salicylic acid from which it's derived, is this group. Okay, it's a painkiller. All the salicylates are painkillers, natural painkillers. So if we have this salicylate here, and we have, say, okay, we're going to put the OH here, and we have the COO there. If we have, actually, we're not going to form an ester with this one. We're going to form an ester with that one for the next molecule. So what we need is an ester out here. I mean, carboxylic acid out here. And on this side, we put acetic acid. Okay. And then all we have to do is condensation synthesis, removal water. So we take an OH and an H, right? That makes water, and we make the connection. Okay. This compound is called acetyl salicylic acid, otherwise known as aspirin. A painkiller. It's also an anti-inflammatory. Okay, my organic chemistry students make that compound in class. All right, so here's how we form an ester. We do it just like I showed you here. The carboxylic acid, we give up an OH and we get an H from the alcohol and we form an ester, right? We remove water, a condensation synthesis reaction, and form an ester. Let's see, acetic acid and ethanol. So we get ethyl acetate is what we'll end up with here, ethyl acetate. Now, if you've ever used whiteout, not the little strips of whiteout, but the bottle with a brush in it, most of those use as a solvent ethyl acetate. And if you smell it, then you know what ethyl acetate smells like. All right. Nail polish removers also sometimes use ethyl acetate. Sometimes they use acetone also, but they have two different odors. You'll recognize acetone separate from ethyl acetate. Acetone is, let's see, is like that. That's acetone. We don't have time to go into the naming convention for these. So don't concern yourself with that one. Let's move on. Fats, right? If you've had a course in anatomy and physiology, or some biology courses will also introduce the topic. A true fat is a triple ester of glycerol and various fatty acids. So here's your glycerol molecule. Sometimes I draw the glycerol like this. This is a shorthand notation or a linear version, but it's easier to see it when you do it like this. It's got 3 carbons, and then it's got OH groups out here, and the rest of them are hydrogens. Okay, that's glycerol. Now, if you get a fatty acid, then you'll have this, right? And then a long chain of hydrocarbon. So it'll go like C, 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 however many you need. In the case of steric acid, you have 17 of them, 17 carbons with bound to carbons in a chain, but hydrogens on either side to make up the 4 bonds. Okay. Now, if you take this and you do a condensation synthesis, right, and form that bond, right, and do that 3 times. And this one, they don't have to be all the same fatty acid. They can be 3 different fatty acids if you want. Now you have a true fat. And that's used in mammals to, well, in lots of animals actually, to store energy for long term. It's very stable and it's very high energy. In fact, you can derive more energy from the same amount of fat than you can from the same amount of carbohydrate. But carbohydrate is more immediate. It goes into action faster. It takes longer to get the fats to come out and give you the energy. So that's why if you eat a lot of starches, the excess starch is going to be converted to fat. The excess sugar is converted to fat. And then it's harder to get rid of that body weight if you convert it to fat. So that's another topic. So we'll move on. Most fats are solid at room temperature. Right? If you cook with Crisco shortening, that's a solid fat. If you cook with olive oil, that's a fat, but it's a liquid fat. So liquid fats are known as oils, and solid fats are just fats. Okay, so we mentioned this earlier. If you have an alkene or an alkyne and you want to saturate it with hydrogen, you can do that catalytically speaking. That's also known as hydrogenation. You're adding hydrogen to the molecule. And some of these, especially the liquid fats, the oils, are unsaturated molecules. Within that long chain, you may have some double bonds in here. It's unsaturated. So if you want to change that oil into a solid fat, then you hydrogenate it. You add hydrogen across those double bonds, and now it's solid at room temperature. Okay, here's an example, cottonseed oil. So let's see, how many carbons do we have here? Let's see, here's the carboxylic acid end. We have 7, 8, 9, 10, 17. So this is steric acid. It's a derivative of steric acid because it has a double bond in it here. This is cottonseed oil. And if you hydrogenate it, you make steric acid, which is used in margarine. Okay. Now, one thing you can do with these fats is instead of condensation synthesis, you can break that bond. And if you break the bond in just the right way, you can produce this glycerol separate, and then you can produce ionic compounds of the acids. And the way we do that is we react the fat with lye, sodium hydroxide. What sodium hydroxide does is it breaks that bond, and it gives you, actually, well, you end up with that and, let's see, that, right, charged with no hydrogen. Instead of hydrogen now, you have sodium. So it's what's known as the sodium salt of the fatty acid. Okay, what good is that? Well, this by definition is a soap, right? If it doesn't look like that, if it was not from the action of lye on a fat, then it's not a soap. This is a very specific definition. And this process we call saponification. reacting a fat with lye, with sodium hydroxide, is saponifies the fat, separates the fatty acid from the glycerol. Okay, so what good is soap? Well, we know, practically speaking, soap is, you can wash your hands, you can wash your clothes, but how does it work? Okay. Remember the concept of like dissolves like. So nonpolar compounds dissolve in nonpolar solvents. So oil will dissolve other oils. Polar solvents dissolve polar molecules. So water is polar, it dissolves ionic compounds. What if you have a polar end to a molecule and a nonpolar end on the same molecule? That's a soap. Right? This part out here is nonpolar. What does that dissolve in? Well, when you put it on your hands or on your clothes, when you wash them, this dissolves in the fat, the oils that are deposited on your clothes when you wear them, and they pick up from the environment. Water will not wash away those oils, right? They're hydrophobic. They will not dissolve. So we dissolve the oils in the fatty end, the nonpolar end of the molecule, and then the water attaches to the ionic end. And that's the bridge between water and the oil, the grease or oil in your clothes or on your hands. And then what it does is it forms, let's see, like dissolves like. I just described that, so I'm not going to stop here. It forms what's called a micelle. The nonpolar end of the molecules dissolves in the oil droplet, and they leave exposed their polar ends, which are hydrated by water. They're solvated. It brings them into solution. And then you wash them away, and that cleans your clothes. There's a problem with soaps, but I'm not going to get into it now. It has to do with hard water. I'll just say this much. If you try to use the conventional soap, as we defined it, with hard water, you get scum. So that's why people in hard water areas have water softeners built into their homes. Okay, another derivative. This is called an amide. And notice that on this side, you have what was probably a carboxylic acid. It's missing the oxygen now, right? And on this side, you have an amine. Okay, so when you get an amine and a carboxylic acid together, okay, carboxylic acid and an amine, which is NH2. Let's do an H here and an H here and some other R group. This is what's called a primary amine. A primary amine only has one R group on it. Secondary amine has two R groups, and a tertiary amine has three groups. So this is a primary amine. All right, all you need to do is condense, remove a water, right? Condensation synthesis. Here's your water right here. Now, what you have is a direct link between the carbon and the nitrogen. 3 bonds, 4 bonds. So we're good. That's an amine. Excuse me, that's an amide. Okay. I'm not sure if we're going to name any amides. we're just saying it's an amine. If we take, let's see, phenacetin to form phenacetin. Okay, so a lot of the amides have common names, or what we call in chemistry trivial names, not systematic names. They do have systematic names. It's just that some of the trivial names are more commonly used. Acetic acid and this amine, right, has 2 carbons on this side and has an amine on this side, and there's a benzene ring. Right? So we condense it, and that makes phenacetin. Okay. Here's another very, very important organic molecule, a derivative. It's called amino acid. Why is it amino acid? Because it has an amine group and an acid group on the same carbon. So if you have a carbon, a central carbon here, which is called the alpha carbon, and you put a carboxylic acid on this side and an amine, let's see, let me remove that. We'll put the amine down here. All right, 1, 2, 3. Let's see, we need a hydrogen here, and then we have an R group there. So this part is the amino acid part, and then you can make a whole bunch of different kinds out of whatever R you put on there. Okay, the simplest amino acid, and now we're getting into biochemistry naming convention. The very simplest amino acid substitutes a hydrogen here. When you do that, your amino acid is called glycine. Okay. If you substitute a methyl group in there, right, now you have alanine. Okay. Let's see, what's another good one? How about this one? What if we say hydrogen here, hydrogen here, instead of saying benzene, benzyl, we say phenyl. Phenylalanine. Actually, it's phenyl because this is the phenyl group. If it was just this group, it would be benzyl, but this is the phenyl group. Phenylalanine is an amino acid. Okay, what's so great about amino acids? Amino acids are used by cells in our bodies and in plants as well to make proteins. So proteins can do a number of different things. Well, what is a protein first? Well, it's a polymer. You string lots of these together and you get a protein. So how do you do that? Well, you take the amine group from the other amino acid and you form an amide bond with this carboxylic acid. So it's NCC, NCC, NCC on down the line, as many as you want, or as many as the cell is capable of making. And then this forms the backbone here, and these functional groups stick out, right? So you usually see it written, the proteins are like this, and then you have functional groups sticking out everywhere. Those functional groups are what defines the character of the protein. Now, when we eat proteins, our digestive system breaks them apart into simple amino acids, maybe some di and tripeptides. By the way, the bond that we're just talking about here is a special kind of amide bond called the peptide bond. So polypeptides are proteins, and they can be broken apart into individual amino acids, and your body then absorbs them and uses them to build the proteins that it wants and needs. It does that with about 20 amino acids. And with just those 20 amino acids, it makes all the different proteins in your body. Now, most of these proteins we can manufacture ourselves. If we can't get them from our diet, we can use smaller molecules and construct those proteins. But there are 9 of them that are considered essential. In other words, those 9 proteins, those 9 amino acids must be acquired through your diet. Okay, enough said about that. This is the linkage that forms. So for this glycine, it's rearranged. The positions are arranged so that we get these amine group on this side of the carbon, alpha carbon, and this carboxylic on the other side, so we can string them together in the straight line. And then the functional groups of the amino acid stick off to the side here like this. Glycine has a methyl group. And if we bond those two together, we get a dipeptide. And here's your, right here is your peptide linkage right there. Okay. So this chart just puts all the hydrocarbons, carbohydrates, and derivatives in one form, in one figure. All right, so it's nothing special, it just puts them all together. Now, I mentioned earlier that the organic compounds were made in plant and animal cells, some microbial cells. But organic chemistry now has advanced to the place where we can engineer and manufacture synthetic organic molecules to suit our needs. For the longest time, everything in your environment, we make our shelters, we make our tools, whatever, we make them from naturally occurring substances. We just reshape them. But since the early part of the 20th century, actually before then, it started, but by the middle of the 20th century, we were really going full steam with engineering and manufacturing shelters and tools and other things from basic small molecules. And we were making synthetics of our own structural desires. Whatever we want, we can make it. In the beginning, we were just duplicating nature, and now we're just going off making whatever we want to. And that could be whatever you build your house out of, your furniture, the clothes you wear, glasses. These polycarbonate lenses are polymers that are made in the laboratory. So these synthetic materials do what we want them to do. And well, in the beginning, synthetic materials were imitations of the polymers and compounds that we would find in the real world outside in nature. But now synthetics have been restricted. The definition is restricted to cover materials that have no duplicate in nature. All right. The first synthetic polymer was prepared by this fellow, Leo Baekeland, in 1907. And he called it naturally Bakelite. And you'll still find Bakelite used, manufactured and used in various situations. It's a very, very good insulator, and it's very strong. It's rigid. So many times what you'll see is on these power lines, when you come to a pole and a cross beam, and a power line goes across that beam, it's fixed to the beam with one of these, it might be white, looks like semi-conical devices that's attached to the cross beam. And then the power line is attached to that thing. Well, it's attached to that thing because that's an insulator. It doesn't conduct electricity, so it doesn't ground itself through the pole. Well, very often that's made of Bakelite, because Bakelite is a very good insulator. That was the first polymer. Now we're able to understanding how the polymers are structured and how we can adjust the environment for manufacturing the polymer. We can tailor the polymer to whatever purpose we want. Synthetic polymers, sometimes we call them plastics. Some of them are called plastics. They can be molded into different shapes. They can be hardened, or they can be softened by certain additives. Most of them have very, very high molecular weights, long chains, many repeating units. Those repeating units we call monomers. Right? So they just repeat each other on down the line. Sometimes there are single monomers that form the polymer. Those are like ethylene. If you create the right conditions, you can cause this to polymerize and form polyethylene. Okay. Or sometimes we can form polymers from two different monomers. We call those copolymers. So nylon is formed that way. Nylon is formed from an amine, a diamine, and a carboxylic acid. A dicarboxylic acid. Okay, so when they polymerize, you get a bond on this side, and then another one of these on that end forms a bond, and then the amine on the other side hooks onto one of these, so it alternates. Right? Acid amine, acid amine. These are amide bonds, polyamides. That's nylon. And nylon was first created at DuPont. I think they were in St. Louis at the time. Well, now there are various ways to form these polymers. Right? One way is called addition polymerization, and the other way is called condensation. Right? We've heard condensation before. Condensation is just where you remove water, form the bond. That's what nylon does. It's a condensation polymer. Whereas polyethylene is an addition polymer. So the next slide should give you a definition of those. You just add one to the end. Just keep adding them on to the end. And they usually involve a double bond. The double bond opens up to form the bond with the next molecule. And they just keep going like that. Okay, so here's our example of an addition polymer where we take ethylene and with a catalyst, which speeds up the reaction, we form polyethylene. So the monomer is this ethyl group. And we represent it with a bracket and an N. And the N can be 1,000, 5,000, 10,000 units, whatever. You can customize your reaction so that you can make short chains or long chains. You can even branch the chains. So this is the simplest of the synthetic polymers, the polyethylene. Teflon is a polymer. It's an addition polymer. And it was first produced by at DuPont by Roy Plunkett and his group. He had help, of course. And it was purely by accident that they created this compound. He left a fluorocarbon in a reaction vessel at high temperature and pressure overnight. I don't know if he forgot about it or he was trying to make something else, but the next morning they came in and they found this gooey white stuff in there. And they dug it out and characterized it and found that it was, they had really done something magnificent. And they just went on from there. They characterized it and gave it a name, called it Teflon, and found out that it was extremely useful for various things. As very high melting point for a polymer. It was very chemically inert, resistant to chemical attack, very strong, had a very low coefficient of friction. Right, that was interesting. That's why we coat our frying pans with Teflon, so our eggs will slide without grease. But one other one that I don't think is mentioned in your book is Teflon played a pivotal role in the Manhattan Project. Right, look it up. The Manhattan Project was started during World War II for the U.S. to develop the atomic bomb. It was called the Manhattan Project because it started in New York, in Manhattan. But it branched out across the country. We had various sites in Oak Ridge, Tennessee, Hanford, Washington was another site. And to get to the point, the purification and separation of isomers of uranium, right? Uranium 235 is combined with uranium 238 predominantly. This one will not fission. It will not produce a bomb. This one will. But this one is about 0.5%, right, of the total. So you have to concentrate it. To make a bomb, it's got to be up 95%, right? So how do you concentrate something that's the same element? You can't do it chemically because they both react the same. You have to do it with some other means, right? They tried, nowadays they use ultracentrifuges because they're different masses. You can separate them in a centrifugal field, artificial gravity field. But the Manhattan Project also experimented with diffusion, right? Gaseous diffusion. Convert these things to hexafluoride, and then you can heat them up and make a gas out of them and push them through sieves. And the lighter one will go through faster than the heavier one. And that's how you separate them. Well, the problem was that these compounds were extremely corrosive. You couldn't even use stainless steel sieves to do the thing, these membranes. Fortunately, DuPont was now producing Teflon, and Teflon was inert to these compounds. So they produced their screens, their sieves, out of Teflon. And there's a building, let's see. I used to live in Oak Ridge. I'm trying to think of which one it was. There was a big factory called Y12, and there was a K. I can't remember what it was. Anyway, these buildings were huge. And this particular one, they had stacks and stacks and stacks and stacks of these Teflon screens. And they would push these gases through at high pressure. And as the gas collected on the other side of they would run it through another sieve. And then they would bleed off part of it and send it back through the sieves. And eventually, after thousands of sieves, you would end up with a highly concentrated fluoride of uranium-235. Then they would just have to remove the fluorine, make the metal again, and combine it in the proper configuration to make a bomb. Okay, addition polymers. We're still on addition polymers. This one in particular is formed, the monomer is vinylidene chloride. So it's like ethylene, only 2 of the hydrogens are substituted with the chlorine. And that changes its reactivity, the way it behaves when you form the polymer. So when you form this polymer, what you get is polyvinyl chloride, PVC. And we make plastic pipes out of them now. Okay. So these are common addition polymers, right? We said polyethylene there. You can do it with polypropylene, the same thing. You just need that double bond. And polyvinyl chloride, we just looked at. There's Teflon. Polystyrene, right? The foam coolers are made with the polystyrene. A number of things are made with polystyrene. Okay, so now for condensation polymers. I mentioned this one earlier. Well, actually, I didn't mention this one. This is, I mentioned nylon. Here's nylon. So hexamethylene diamine, right? This is the amine. This is the acid, adipic acid. So it has 6 carbons. This one has 6 carbons. And they condense by removing water and forming this amide bond. So there's your polyamide. This previous one, this terephthalic acid, is a benzene ring with 2 carboxylics on it. And then it's copolymerized with ethylene glycol, right? Just like the antifreeze. And it forms PET, actually PETE, polyethylene terephthalate. And everybody knows that one, right? Your pop bottles are made out of this stuff. And its recycling number, I think, is number 1. Okay. So nylon was first introduced at the World's Fair in New York in 1939. So very soon after, let's see, hold on a second. Very soon after, I think nylon was discovered before Teflon, but the development and introduction of nylon took a couple of years. So let's go back to where we were. So nylon was preceded Teflon in discovery, and nylon was introduced to the world at the New York World's Fair in 1939. And you can make different types of nylon, right? It just depends on what form of dicarboxylic and what form of diamine are used in the process. Nylon is one product from nylon is Velcro. Right? The way you manufacture it produces either hoops or loops. So you have hooks on one piece and hooks on the other, and bring them together and they grab each other. That's Velcro. And that's it. We're done with chapter 14, organic chemistry.